Welcome to a brief, succinct video on demand that introduces you to IPv6 technologies. We're all about being at the command line, as you know, in these video on demands. But here's one where we're going to leave the command line aside for a moment, and we're just going to go ahead and take an overview of key new IPv6 features. So let's just sit back and relax as we're introduced to some key components about the IPv6 protocol. We here at Netmaster Class feel that an excellent approach to learning IPv6 is to leverage the knowledge you already have in IPv4. We're going to see many similarities between the two protocols as we master the various features of IPv6. Many people say that, boy, when is this going to take place and what's going to happen to IPv4? Well, first of all, for those of you that have spent many hours mastering the version 4 IP protocol, have no fear. IPv4 is going to remain in place for a very long time as the transition is made to IPv6. There are rich backward support capabilities for IPv4 in IPv6, so the transition can be very gradual and non-disruptive, not only to our own private internetworks, but the great public internetwork that represents the internet. A lot of students ask, okay, well, when will it arrive? We've been hearing about it, seems like forever, but when is it really going to arrive? Well, obviously, companies that have many individuals, countries that is, like Japan and Asia Pacific, they're already aggressively pushing for adoption because they're suffering with the address depletion issues much greater than anyone else is. As a matter of fact, Japanese governments are currently subsidizing private corporations to make the move to IPv6. In North America, we're starting to see pushes to make the move, and this includes the Department of Defense, which has now mandated that it will ensure all of its systems will be running IPv6 by 2008. So we're seeing more and more of a push for this new protocol as each month passes by. What are the issues with IPv4 that necessitate IPv6 technology? Well, by far, the most thought about one, the most spoken of one, is the fact that the addressing space of IPv4 is depleted. We created an IPv4 address space, and then we gave away almost all of it, and are currently facing depletion issues as a result. Another issue with IPv4 is the size of the non-default internet routing tables. As more and more nodes come online, the internet routing tables grow, and this necessitates a lot of horsepower and a lot of overhead when it comes to manipulating and using these internet routing tables. The other issue with IPv4 that drives us crazy is that we've patched it to deal with address depletion, and one of the patches, as you know, is network address translation. And when we do network address translation, we're hiding the true source of traffic, and this is a problem. The internetworking and the internet technology is supposed to be end-to-end, and there are a lot of great advantages for having an end-to-end type infrastructure, and all these tricks we do because of address translation or address depletion issues, that's going to break this true end-to-end model that we so desperately want with TCP/IP. But please, when it comes to IPv6, realize then that it's more than just about address space depletion. Certainly, one of the main features of IPv6 that we're excited about is a 128-bit address that is going to open up the amount of address space massively. One statistic I saw was like 10 to the power of 28 times 5 for every person on the planet or something like that. So there is going to be an amazing number of addresses with a 128-bit address in use. And they're also going to do something smart this time and only deploy about 10% of the overall space. so 90% of the space will be waiting in the wings when needed. We love the fact that with this larger address space, we can eliminate network address translation and we can get internetworking back to an end-to-end type of infrastructure. Routers will behave and will be able to route more efficiently. We'll look at why that is in other video on demands. IPv6 is not going to rely on broadcasts. In IPv6, broadcasts are eliminated, and instead we have Unicast, multicast, and anycast type technologies. No more need for a broadcast. One of the great things we love about IPv6 is the transition-rich features that have been built in so that we can smoothly and seamlessly transition to this new technology from IPv4 environments. Mobile IP support, which was an add-on to IPv4, is built right in to IPv6, and IPsec, which was an add-on for IPv4, is built right into the IPv6 protocol. So we're getting the sense here that, boy, there are a lot of advantages we can take with IPv6 beyond the bigger address space. In fact, we at Netmaster love to recognize the flexibility that many of the IPv6 features are going to bring us. We'll take a look at stateless auto configuration. This is getting your address information, but in a stateless manner. Where DHCP traditionally in the past was stateful, the DHCP server had to maintain information about the client state. In IPv6, we have a much more flexible way to disseminate the needed information in a stateless auto configuration approach. Also, anytime we need to renumber an area, that's going to be built into the IPv6 protocol, and we can even do valid and preferred times for complex but easy to implement renumbering schemes. Interfaces in IPv6 can have multiple addresses assigned to them. And these are not secondary addresses, they're just multiple addresses that you can assign to any interface. Our interior gateway protocols are going to use special addresses that are created by the router on the interfaces, and this is called link local addresses. And these link local addresses that automatically get created are those addresses that are used for interior gateway protocols. For instance, next hop addresses in the IGPs reference the link local address, and that's going to give us a lot of flexibility, as we'll see, especially when we get into the video on demands regarding IGPs and IPv6. Also, when it comes to the addressing, we can utilize provider-dependent or completely provider-independent addressing schemes in our infrastructures. So I hope you've enjoyed this introduction, and I hope this has really gotten you excited for the video on demands that will follow, where we will configure many of these features. And please remember that we're going to constantly leverage our knowledge of IPv4 as we master IPv6. Hello and welcome to this class on demand involving IPv6 addressing, and this is IPv6 address structure, address types, and also we're going to take a look at IPv6 versus IPv4. This is a great kind of framework for you to begin studying IPv6. Take a look at how it's different, how it's similar, etc. Well, certainly one of the most famous components of IPv6 has been already the IPv6 address. And here we can see an IPv6 address in all its glory. Remember, it's a 128-bit address, so representing it in dotted decimal, as we have with IPv4 addresses, would be quite cumbersome. The IPv6 128 bits is going to be depicted for us in terms of hexadecimal. So as we look at this long string of hexadecimal digits, this is the IPv6 address. By the way, having a 128-bit long address is going to accommodate for many, many more addresses than with the IPv4 addressing approach. As a matter of fact, there are many different ways that have been publicized for indicating the number of addresses that this is going to provide. By far, I think the most exciting way to look at this is just to look at per person on the planet. There will be, given this address structure, approximately 5 times 10 raised to the 28th addresses for every person on the planet. By the way, the writers of these standards aren't saying that this is the last version we'll ever need or the largest address space we'll ever need, but they are saying it should accommodate us for the foreseeable future, and I think we would all agree. Also, what they're going to do, quite clever, compared to v4 where they created the address structure and then assigned almost all of it, leaving very few addresses aside for experimentation, with IPv6 they're going to take the exact opposite approach. They're going to leave about 85% of the address space completely unassigned, and they're only going to assign out a small percentage. This has obvious, great implications for future developments of the protocol. As you look at this number of addresses per person on the planet, you may say, well, it's kind of ludicrous that they made the address space this big. But please keep in mind the future of IP and how our definition of a site may change. Right now, we consider a site typically like an organization with all their workstations and things inside it. But in the future, a site may be, I saw a presentation at one of the Cisco Networkers conference where they were showing a modern day soldier for the U.S. Army, and a site, a TCP/IP site, was his rifle. And there were many different IP addresses on this rifle that was their consideration of a site. So please just keep in mind that as technologies change, we'll need more and more addressing, and maybe even per person on the planet. Now, the IPv6 address, even though it's in hexadecimal to represent the 128 bits, it is still a bit cumbersome. Therefore, they have introduced some syntax tricks that we can utilize. For instance, look at this address. One of the things we note about this address is that there's a lot of zeros in it. Some of the fields contain nothing but zeros, and then other fields have zeros to begin the field. Look at the second field, for instance. It's 0008. Well, obviously, there's got to be something we can do to represent this a bit more efficiently, and there is. The first syntax trick you need to be aware of is you can take any leading zeros in a field and you can omit them. So I have done that to shorten this address. Look at how that address is much cleaner down below. Notice in the second field we omitted the leading zeros. Then in the, let's see, it's field 4, 5, and 6. In the 4, 5, and 6 fields, we omitted the leading zeros, leaving just a zero in those fields. And then finally, in the 7th field, we trimmed off the leading zeros there as well. So this is the first addressing syntax trick we have to make these addresses represented more cleanly. Thankfully, that's not the only trick we have. We have another powerful IPv6 syntax trick, and that is whenever we have just successive zeros in the address, here you can see fields 4, 5, and 6 are all just zeros. Once within the address, we can represent those with a colon. So notice here I've actually combined both syntax tricks for the cleanest possible representation of this address. We've trimmed off the leading zeros, and then we have given all of those successive zeros a representation of colon. Please keep in mind that with the colon, you can only do that once in an address. So if you've got two areas where there's nothing but zeros, please keep in mind you can only use the colon trick just the one time. By the way, you may be wondering, is the Cisco operating system going to handle these addressing syntax tricks? Absolutely. Let me go down to the router interface here, and let's just create a loopback address of 100. Don't you love loopback addresses? Anytime you want an address or an interface on your router, you can go ahead and just create one thanks to the virtual loopback address. They're great for experimentation, among other things, in the operating system. So I'm going to create an interface loopback 100, and I'm going to say IPv6 address, and I'm going to say 2018:8:5A3:11:7334. Now, let me do context-sensitive help here. We see that so far, so good. It's accepting this address just fine, but something else that it's going to want is the prefix length. We'll talk more about that in a moment. So we are going to have to indicate prefix length. I'll just say /64 here and hit enter, and we're done. We have just assigned that IPv6 address to the interface, and my big point here was that notice the iOS is just fine and it completely understands these address syntax tricks. So that's a great feature. Let's say no interface loop 100 and we'll get rid of that loopback interface that we just created. Alright, so great that we have those syntax tricks that we can use to make these addresses more manageable for us to work with. Something else that we just saw in the router interface was the fact that subnet masks are addressed with CIDR, or prefix length notation. That is the format that we are now going to use. And that's great. We've been getting very used to this format with IPv4, and now it is the exclusive format that we're going to be using in IPv6. Notice this particular address, we have 2001:8, we've trimmed off some zeros there, 85A3, and then we've got : So it looks like all zeros following this address, and the first 64 bits of this are going to represent the network portion of the address. Kind of interesting. You wonder, where is the end of this? It's just all zeros. Where's the interface identifier? Well, that's exactly what we're going to be discussing next. Just like IPv4, with IPv6, you're going to have a portion of the address that represents the network, and then you're going to have a portion of the address that represents a host on that network. One of the great things about IPv6 is that you can certainly manually assign a host identifier like we do in IPv4, but you can do something much neater than that. You can have the operating system automatically calculate for you the host portion of the address and make it unique. This is called the EUI64 addressing approach, and here I've highlighted for you the last 64 bits of the address that are this EUI64 bit portion. What it does is it looks at the router. When you say you want to do this, it looks at the layer 2 address on your system, and from that layer 2 address it automatically calculates you a interface ID or host ID. So what a neat trick. We can use the modified extended unique identifier EUI64 addressing approach to automatically provide a unique identifier for the host portion of the address. How is this done within the operating system? Let's go down and take a look. Let's go ahead and create another loopback address. We'll just keep picking on interface loopback 100. And let's go ahead and try giving an IPv6 address this time, but having that host portion created automatically. So I'll say IPv6 address 2001, and then I'll just say 8. We can trim off those zeros. 85A3:4289. Okay, and there's my 64 bits. I'm going to say : /64. Now I'm going to space and do some context-sensitive help, and look at this. We can go ahead and we can specify EUI-64 here, and we will have it create for us that host portion. So I'll say EUI-64. By the way, we're going to have more to say on this in future video on demands where we are manipulating addresses, but we're getting a great preview of this feature now. So I'm going to say enter there, and wow, I just created a full-blown unique IP address for this interface, and I didn't have to worry about the interface ID portion whatsoever. All I did was supply the network prefix, and the operating system did the rest. Let's do an end, and let me do a show IPv6 interface loopback 100. Notice how that command is almost identical to the IPv4 version. I could say show IP interface loopback 100 in IPv4. Here I'm saying show IPv6 interface loopback 100. When we do look at the IPv6 interface characteristics, look at this. It says IPv6 is enabled, and then it says you've got a global Unicast address assigned here, and it is 2001-885A3-4289. That's everything that I gave it. And then look at what the operating system gave it. 217-95FF-FEAD-1A10. Pretty cool. Then it even shows us, hey, your subnet is the first 64 bits. And look at this. It reminds us that your interface ID portion came from the EUI standard. So that is very powerful demonstration there of how we are automatically assigning the host portion with IPv6 using the EUI format. The typical IPv6 address is going to consist of a 64-bit network portion and a 64-bit interface ID, as we just saw. Further breaking down the 64-bit network portion, we're going to see that we have a 48-bit global routing prefix, typically, and then a 16-bit subnetting portion. So imagine that my corporation will get a IPv6 address space, public address space, let's say, and I'll have that 48-bit global routing prefix, and then I'll have a 16-bit subnet ID portion. Wow, so we can create tens of thousands of subnets when we're given this address. So this is just fantastic. Plenty of address space for subnetting with a 16-bit subnet ID. Let's take a look at the types of IPv6 addresses that we're going to be dealing with. We can create, and you've seen me doing it, globally unique unicast addresses. And this is very comparable to what we're used to in IPv4. One difference here is with the global unicast address, we've seen we can automatically have the host ID portion calculated. Something else that we have, just like in IPv4, is multicast address types. These are obviously more efficient than a broadcast approach because we're only going to be sending the traffic to those multicast recipients that have subscribed to the traffic, that have an address that has joined the multicast group and that want to receive the traffic. Here you can see FF02:9 address. IPv6 address types, Anycast. So we've had unicast, we've had multicast, and now we've got something called Anycast. With an Anycast address, you're going to assign the same address to all the interfaces on, let's say, 3 devices, and you are then going to have traffic sent to the closest by metric value receiver. So a router is going to decide, oh boy, I see that I have 3 devices out there, maybe they're servers, and all 3 server interfaces have the same Anycast address. It will decide who is closest and send traffic to that closest recipient. In the command line, you may have remembered when I did a question mark after our address, one of the options was Anycast. So we can make any address an Anycast address. Any global unicast address can become an Anycast address and can behave this way. Now, of your unicast addresses, there are some special ones that we want to bring up. First of all, there's the global unicast address. You've seen me assign one of these. In fact, it's still visible to you down below. There is, as you can see in the output, my global unicast address. Now, there is also something called the link local address, and I've depicted one for you up here in the graphic. They begin with FE80. Whenever you enable IPv6 on an interface, a link local unicast address is created for you. Wow, interesting. So whenever you enable and put on a unicast address, you're also going to have another address, and that is an address unique only on the link, and it is used for communicating only on that link. This comes in handy for such things as auto address configuration or neighbor discovery. So very interesting. On this loopback 100 interface, we have a link local address that was automatically created for me, and then we have the global unicast address that I created for global unicast routing purposes. We can also have things called embedded IPv4 addresses. This is when we take an IPv4 address and we embed it right inside a v6 address. And a site local unicast address. A lot has been made of this lately, but I want you to be aware of something. While it is true that they originally took some address space and set it aside for private use only, just like they did with v4, this whole concept has been deprecated. The reason why they don't want to, going forward, use a private address space with IPv6 is, number one, there's no need. There's plenty of addressing. We don't have to set any aside as private. And number two, remember, they want to do away with network address translation. If they introduce private address space, that is going to probably reintroduce network address translation, and that's something that they don't want companies to have to do. We don't want to break the end-to-end design of the internet. So they have deprecated the idea for site local unicast address space. Let's go ahead and end this video on demand by just taking a look at how these addresses are similar. And it shouldn't cause you a great fear or, please don't feel like you just aren't going to be able to deal with these large IPv6 addresses. They are very similar to their IPv4 counterparts. To prove that, watch. Look at these addresses, 172.16.12/24, 172.16.13/24, all the way through 15/24. If we were to convert these to binary, and we were to come up with a summary address, we would come up with 172.16.12 with a /22 mask. That's the perfect summary for those v4 addresses. Well, guess what? From a binary perspective, we can do the same exact thing with IPv6. Remember, they're both binary addresses, v4 and v6. We're just coming up with two different ways to represent them. If I take v6 addresses and I do 172.16.12.0 and a 24-bit mask, it would come out to, in hex, AC10:0C00 with our 24-bit mask. That's 12. The one below it is the 13. The one below it is the 14. The one below that is the 15. And look at our summary. Sure enough, it is a 22-bit summary, just like we saw before, because from a binary perspective, these are the same address. So, this is a very interesting comparison where, binarily, if you will, these are the same address, and we shouldn't let this freak us out too badly, this 128-bit address. As a matter of fact, let's go ahead and demonstrate this in action on the router. Watch this. I'm going to do a show IP interface brief here on R1. And you can see what I've done here. I have put these addresses on the router. There's 12, 13, 14, 15. Okay, I've assigned these on the router. As a matter of fact, if I do a show IPv6 interface brief, you're going to see that I have also put the IPv6 versions of those addresses on the router. We're running OSPF between R1 and R2, and they're in different areas. If I go over and on R2, I do a show IP route OSPF, we're going to see we have all of the v4 subnets. If I do a show IPv6 route OSPF, we're going to see that we have all of those v6 networks. Now, let's have some fun. The debug IP routing command is awesome. Pretty safe debug command, and it'll show you any changes that happen to the routing table. I'm also going to turn it on for IPv6. So let's turn on IPv6 routing debug. Another safe command that's going to show you any changes that happen to the routing table. These are commands that you definitely may want to consider during your CCIE lab exam. Very safe, very powerful debugs that'll watch the routing table for you and will communicate via syslog messages any changes that have occurred in the routing table. Okay, let's go over to R1 and let's do this. Let's go into the router process for v4 and let's do the summary. So we are going to go in to that process and we are going to type in the summary. The summary syntax would be area 1 range 172.16.12.0 with the address 22-bit mask 255.255.252.0. Look what's happening over here on R2. All those individual subnet entries are being deleted from the routing table. Delete, delete, delete. We added the summary and we deleted all those individual entries. If I do a show IP route, OSPF, we see we just have the single summary entry. How about in the v6 world? Identical. Watch this. I'm going to go IPv6 router OSPF1, and the command is almost identical to do the summarization. Area 1 range, and then we're going to provide the summary with that same 22-bit mask. And when we come over and look on R2, look at the debug output we have. Sure enough, the summary was added, and then we have delete, 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 delete as the specific subnet entries were deleted. If I do a show IP v6 route OSPF, we see we just have that single summary. So, I hope you get a sense for the overwhelming number of similarities that we're going to have with v4 and v6, and we can leverage all of that wonderful v4 education that we have in v6. Are there going to be differences? You better believe it. For instance, we saw a difference today. Show IPv6 interface loopback 100. One of the major differences that we saw today was, hey, look, there is a link local address that we have to master and that was assigned to this interface kind of magically. And look at this. It joined some multicast groups. What are those multicast groups that it automatically joined, and why are they used? So yeah, there are some key differences that we're going to have to master about v6, but I hope you realize after this video on demand that there's a lot we can leverage from v4. Thank you so much for attending this video on demand, and I look forward to seeing you, and I put that in quotes since I can't actually see you, but I look forward to your attendance in more of these v6 video on demands. Welcome to another video on demand in block 1 of the IPv6 series from Netmaster class. Here we're going to look at IPv6 address assignment methods, and we're going to be focusing on static assignment of IPv6 addresses. Now you might think this video on demand is going to be over in about 30 seconds. This is easy. In fact, we've seen it in previous video on demands where we're going to use the IPv6 address command to statically assign an address. But there's a little more to it than that. And there's some really fun things to see that happen on an IPv6 speaking router with these addresses. Notice that we'll be looking at both routable addresses and we'll also be looking at link local addresses in this presentation. Now, this is a decision diagram that was designed by Netmaster class to show you the almost overwhelming number of options you have when it comes to getting an IPv6 address on an interface. Notice we immediately branch off and want to start talking about link local addresses. And remember, those are always going to start FE FE80. We should burn that into our brains. Whenever we see an FE80 prefix, we know we're dealing with a link local address. And we contrast this to routable, global unicast routable address assignment. Notice that there are static and dynamic methods for assigning both types of addresses, and we're going to be looking at all of these throughout the video on demands. This video on demand will focus on static assignment, as we mentioned. We'll first look at routable address assignment, and then we'll look at link local address assignment. Well, first, let's talk about the static assignment of routable addresses. I'm going to go to an interface, and I'm going to assign static IPv6 address to the interface. And one of the options you get right off the bat here, obviously, is are you going to manually assign the interface or host ID, or are you going to use the EUI64 method of automatically generating the interface ID portion? Please note that when you're studying, it's probably going to be useful to you to avoid typos and to ease your working with the routers to go ahead and not use the EUI64 methodology. So we can go to an interface, and as you can see I've done here with this address on screen, we can assign the interface ID. Here I'm just literally making this the .1 router, if you will, with a 64-bit prefix. Obviously, in the CCIE lab exam, read the task requirements carefully, since they may force you to use EUI64 addressing. If they don't care, if they give you the option, obviously to avoid typos, you may want to go ahead and manually input the interface ID, as I've done in this example. Something else that we're going to see here at the router command line is that with IPv6, there is no concept of secondary addressing. You can assign as many addresses as you like to an interface, and we'll actually show you that at the command line. In fact, let's get down to the command line right now, and let's see some very interesting things just surrounding the static assignment of addresses. One of the first things that I'm going to do on this router is I'm going to say no IPv6 Unicast routing. So I am turning off this router's routing capabilities for IPv6. We are initially going to look at this router like it's an N system. Okay? The next thing I want to do to make this demonstration more interesting is I want to turn on a debug here. And the debug that we're going to turn on is the debugs associated with neighbor discovery. So we're going to say debug IPv6 ND. So we're going to turn on ICMP neighbor discovery event debugging. This is very interesting and is going to show us the replacement for ARP technology that exists in IPv6. ARP has really gone away in v6 and has been replaced by functionality built into ICMP, specifically this neighbor discovery process. Okay, let's now go to an interface and let's configure the IPv6 address. Let me do a show IP interface brief, just to remember what interfaces I've got on this router. Oh great, we have an E0 interface. That'll be perfect for our purposes here. So I'll say interface E0, and now I will statically assign an IPv6 address. Very easy to do. I say IPv6 address 2001:1:1/64, and I have just assigned an IPv6 address on this interface. Notice that I have manually input the interface ID. Another option would have been to just say ::/64, and then we could use EUI-64 at the end, and that would automatically generate the last 64 bits of the address. But I'm going to manually assign. So we'll say .1/64 in order to do the IPv6 address assignment. And now notice we're getting some debug output. First of all, we get some of these neighbor discovery debugs. And ICMP-v6 neighbor discovery process says we're adding the prefix 2001 to Ethernet 0, and we're sending a neighbor solicitation for that particular address. Look at that. We're sending a neighbor solicitation. It's soliciting the link and getting receipt from duplicate address detection that our address is unique. Wow. So neighbor solicitation kicks in and ensures that we have a unique address assigned to this interface. I like it. Now look what happens. Once we find out we're unique, we send a neighbor advertisement for our address. Neighbor advertisements are used anytime there is an address change on an interface. So here we've changed it from not having an address to having an address, so we send a neighbor advertisement. Now it looks like the address is fully up and established on the interface, and then we received a router advertisement. We are obviously connected to a router on this link, and that router is sending us its link local address. We'll talk more about router advertisements and their usage later on in other VODs. So this is very interesting, this process we see being carried out here on this particular interface. And these debugs are fascinating to look at. There's a couple of things that I want to investigate here that just happened on this interface now that we have assigned this routable address. Let me do a show IPv6 interface E0. Notice this is almost the exact same command as the previous version of IP. I would have done a show IP interface E0. Instead, I do a show IPv6 interface E0. When in doubt with IPv6 commands, just replace the keyword IP with IPv6, and you should be good to go. The first thing I want you to notice in here is that when we assigned the global routable address, please realize that this link local address is going to be dynamically generated. IPv6 speakers use link local addressing for many different functions, and we can see that happening here right at the command line. We can see how it's a necessary ingredient for IPv6. Also notice that we have joined some multicast groups. FF02 indicates they are link local multicast groups. And one of the groups we have joined is FF02::1. This is the all subnet hosts address. If I go in now and I make this router actually look like a router with the IPv6 Unicast routing command, we should see some things happening right away here. First of all, remember earlier we received routing advertisements? Now we are sending routing advertisements. And it looks like we're communicating MTU and prefix information. We'll cover this in detail in later video on demands. But notice now we're acting like a router and we're sending router advertisements. Let me rerun that show interface command. And we notice that something's changed here as well. Before, we had joined FF02::1, the all subnet hosts multicast address. Now we have also joined FF02::2. You probably have already guessed what multicast group we just joined. It's the all routers on the subnet group. So now we're part of the all routers on subnet multicast group. And notice all this ND information has been added to the output. We now have these neighbor discovery router advertisements, how often they're sent, how often they live for. Again, we'll cover all this in later VODs, but we can see these changes that have occurred with the IPv6 Unicast-routing command. Okay, I'm going to go ahead and turn off all the debugging so we're not bothered with debug messages as we do further demonstrations here. By the way, while we're here, let's cover this concept of secondary addressing. If I do a show run interface E0, you'll see that we have an IP address assigned to this link, and we have an IPv6 address assigned to this link. If I were to go into global configuration mode and then say interface E0, IP address 20.20.20.1, what happens? We overwrite the IP address on the interface, don't we? If I do a do show run interface E0, we'll see that we have overwritten the IPv4 address on that interface. In fact, I don't want to do that, so I'm going to change it back. IP address 10.10.10.1. Now watch this. Let's add another IPv6 address and see what happens. IPv6 address 2001:1:1/64. Now let's try a do show run interface E0. Different behavior in IPv6. Notice we don't overwrite the existing IPv6 address that exists there. We add another globally routable address to the interface. No concept of secondary addressing in IPv6. We can just add another primary address, if you will, to the interface. One of the things you might get a little queasy about right now is, my goodness, what would determine the source of IPv6 traffic then coming from this interface? Is it going to use the 2001 address or the 2002 address? Well, no need for us to get into details about this now, but just so you know, the answer lies in RFC 3484. And that RFC 3484 is titled, appropriately, Default Address Selection for IPv6. Well, lots of fun stuff to see. I hope you enjoyed that demonstration on the topic of static assignment of these routable addresses, and I hope we learned a lot there. Something else that we have the ability to do in IPv6 is use IPv6 Unnumbered. It's a lot like the IPv4 unnumbered functionality. The interface you reference has to be in the up state, and that interface is going to be reported as the source of traffic. Let's do a quick demonstration on this on the command line. It's very simple, but worth demonstrating. Let me create an interface loopback 10. And let me say IPv6 address. We'll go ahead and give this loopback interface an address of 2001:1:10/64. Again, not using the EUI-64 for the interface ID. I'm manually configuring it. Oop, can't use that prefix again. Oh, no problem. Let me go 2003. Okay, so 2003:1:10/64. So we've just assigned an IPv6 address onto this loopback interface. Now, if I go to another interface, for instance, interface serial 0, I don't have to give this interface a specific address. I can reference the loopback address. Watch. IPv6 unnumbered loopback 10. And it accepts this. And it says, okay, I need an IPv6 address, and no problem, I'm just going to go ahead and borrow the address that is assigned to the loopback 10 interface. So we have unnumbered functionality here in IPv6, and it works almost identical to the unnumbered functionality we're used to from v4. Let's go ahead and conclude this look at static address assignment in our v6 world by looking at the link local addressing. One thing that we have to realize about the link local addressing is, yeah, by default, it is dynamically assigned. But we have the ability to statically assign these link local addresses as well. And when we statically assign them, we can use EUI64 or we cannot use EUI64 for the interface ID, just like our regular routable addresses. Amazing. Let's take a look at this. Let me end this configuration here, get back to privilege mode, and let me do a show IPv6 interface E0 once again. And if we scroll up here, we remind ourselves, okay, we have actually 2 global Unicast addresses assigned to this device, and we have only the one link local address that was automatically generated for this link. Now, one of the issues with this address is I'll never know what it is. I mean, I can certainly see it in this show output, but boy, it'd be something that would be tough to memorize. The only thing I know for sure about the link local address is that it begins with FE80. Other than that, I don't know that address. Well, we can statically configure the link local address, and that's what we want to show you now. I can go into the interface E0, and I can say IPv6 address, and I can say FE80::1, and do my context-sensitive help here, and look at that. I can say link local. Imagine that. We redefine the link local address that's on this interface statically, overriding the dynamically assigned link local address. Let me do a show IPv6 interface E0, and we'll see if this worked. We'll scroll up. We'll check our IPv6 link local address, and sure enough, we've overwritten it as FE80::1. Can you think of any reason why you might want to do this? Sure. Now you very definitively know the link local address that is assigned to this particular interface. And you'll see as we get later in deeper into these video on demands where it may be beneficial for you to know off the top of your head the link local address that is assigned to a particular interface. I hope you enjoyed this video on demand, and we look forward to teaching you much greater and broader IPv6 principles in later videos. But as you can see with IPv6, a lot of interesting things happening even with just static address assignments. In this presentation, we are going to be reviewing the IPv6 dynamic prefix assignment method known as stateless auto configuration. In this presentation, we're going to be using 2 routers. We'll set up one router acting as an IPv6 stateless auto configuration client, and we're going to have a second router acting as an IPv6 stateless auto configuration router for that client. Both of these routers are going to be attached to the same common network. The key iOS configuration commands that we're going to see in this particular video on demand include on the client end station the IPv6 address auto configure command. That'll literally look like this. IPv6 address auto config. That's going to be an interface configuration command that we'll see. On the auto configuration router, we're going to use the good old IPv6 address command. So simple commands, but that IPv6 address autoconfig command might not be one that we have necessarily seen before. We're also going to look at some show commands, including show IPv6 interface, a great command that we've seen in previous VODs, and this is a new one, show IPv6 routers. The show IPv6 routers command is going to be very critical in this particular video on demand. One of our favorite debug commands from IPv6 we're going to see again, and that's debug IPv6 ND for neighbor discovery. To get started, let's go ahead and remind ourselves of our decision diagram when it comes to IPv6 address assignment. Remember, there were plenty of options for statically configuring addresses, and there are options for dynamically configuring them as well. For instance, we can allow the link local address to be dynamically assigned just by enabling a global unicast address on the interface. When it comes to dynamically assigning the globally routable address, notice we have a couple of options. One is DHCP version 6, and we'll cover that in an upcoming video on demand. But the one we wanted to focus on in this particular VOD is the stateless auto configuration option. Well, without any further ado, let's go ahead and get started in demonstrating the stateless auto configuration feature. Notice we have R1 and R2, two routers connected by a simple Ethernet interface. And what we want to do first is we want to go to the IPv6 router that is going to be acting as the stateless auto configuration client. We're going to go to this particular router, and we are going to issue the command debug IPv6 neighbor discovery. So we want to turn on the neighbor discovery event debugging. And then what we'll do is we'll go in and we'll issue the IPv6 address autoconfig command, and we'll see what happens. So let's go into the E0 interface, and we're going to say IPv6 address autoconfig. This may be a new command for many of us. Might not have seen this before. Now, what's going to happen is we are going to configure ourselves with a link local address. So we have our interface configured with the link local address, and notice we go through the ICMP testing process to ensure that this address is unique on the link. We've seen this in previous VODs. We do this neighbor advertisement, neighbor solicitation, duplicate address detection process, and notice that the link local address that is come up with is determined to be unique for this particular link, and it is our assigned link local address. Then what we do is we send some router solicitation messages. We are desperately looking for a router on this link that can provide us with our prefix assignment from which we can generate our interface ID. We're looking for the router on this link that will provide us with our IPv6 address configuration. Now notice that we have not activated yet the R2 router on this link. So these messages are going unanswered, as we can see from the debug output. One of the keys to actually activating the R2 router on this particular link is going to be to use the IPv6 Unicast routing command. Right now we have R2 just sitting there, and in fact we don't even have IPv6 enabled on this Ethernet interface. So these router solicitation messages are sadly unanswered here for R1. Before we leave R1, let's go ahead and do a couple verification commands. We can see things aren't looking good, but let's just make sure that R1 isn't having any luck. Let's do a show IPv6 interface E0, and let's look at the IPv6 parameters for R1. Yeah, sure enough, things aren't good here. Yes, we do indeed have that link local address that we saw verified in the duplicate address detection process, but sure enough, we have no global unicast IP address configured. Also, this is a great verification command for this feature. Let's do show IPv6 routers. And notice there is absolutely no output for this command. We do not have any router out there providing us with our stateless auto configuration. Okay, so let's go over to R2 now, and we'll start over there the same way. We will debug IPv6 neighbor discovery, and now we'll go ahead and go to the Ethernet interface in question, and we'll say IPv6 address 2001.1001:1/64. Now, this should be all that we need to do in order to go ahead and begin providing auto configuration for anyone on the link, or is it? We see that we're adding the prefix and sending our neighbor solicitation. We're doing the duplicate address detection for our link local address. We're doing the duplicate address detection for our Unicast address, but nothing by way of stateless auto configuration. And as you can see from our slide, what's missing is the IPv6 Unicast routing command. So we are indeed missing a key command here that is going to enable us to provide the router with its stateless auto configuration. Let's go ahead and issue that command, IPv6 Unicast -routing. And the minute we do that, we see we are meeting with success when it comes to the stateless auto configuration. Look at, I am now sending a routing advertisement to FF02:1 on E0, and I am providing the prefix that machine is looking for. If we go over here to R1, we should see in the debug output that we are receiving a router advertisement from a particular system. It provides a link local. We're deleting some stale information, it looks like, and then we're auto-configuring the address and then going through the duplicate address detection for this auto-configured address. Let's do show IPv6 interface E0, and this time look at what we see. We have our link local address as before, but now we are being provided with a global Unicast address. Here is our subnet for that particular address, and we can see clearly from the output that this is a result of the auto-config feature. Notice there is a valid lifetime and a preferred lifetime, and we'll get into the manipulation of these values in a later VOD. Notice also that we have a default router listed here in the show IPv6 interface output. That default router is the link local address of R2. That is indeed the router that is providing our auto configuration information. Let me do this. Do show IPv6 routers. And when we do a do show IPv6 routers now, we see, yes, our default router that's providing us with information is at the following link local address on Ethernet 0. We can see when we got our last update. We can see the particular auto-config prefix. And again, we can see the valid lifetime and the preferred lifetime values. Notice how valuable the debug IPv6 neighbor discovery command is for learning the dynamic and even the static address assignment methods and learning the fundamentals of how these particular commands operate. By the way, we can further our understanding in this particular demonstration by going over to R2 and by removing the IPv6 Unicast routing capabilities and observing the messages. If I go ahead and remove that Unicast routing feature, one of the things we see on R2 here is that we just sent, I love this syntax, the final router advertisement on Ethernet 0. On R1, it's going to receive this final router advertisement, and notice it's going to have a 0 lifetime and performs a delete on the router advertisement. What's the effect of this delete operation that we just got from R2 when we removed its capability to be the auto configuration router? Well, let's go ahead and take a look at show IPv6 routers. If we do show IPv6 routers on R1, sure enough, the information has been removed and deleted. So we don't see any default router information listed anymore for our auto configuration. How about do show IPv6 interface And that, of course, is for Ethernet 0. Well, notice in this particular output that it looks like we still have a prefix, don't we? We still have a global unicast address, and we have an auto configuration prefix that's listed. But notice the default router reference that used to be down the end here of the display is gone. That's been deleted. This is the result of the receipt of that router advertisement with the 0 lifetime. But notice the prefix is advertised by R2 as still valid and preferred, and it's still being used. Why is that? This is because the prefix was originally advertised with a valid time of 30 days. That's right, 2,592,000 seconds, I believe, giving us 30 days and a preferred time of 7 days. We'll cover the precise differences between the valid time and the preferred time of a prefix in another video on demand. Suffice it to say for right now that the prefix is still going to be used by R1 for another 30 days, provided that the interface does not go down. If the interface goes down, the prefix assignment will be deleted and lost. So, very interesting behavior we see here, both bringing up the auto configuration and, in this case, attempting to delete the auto configuration information. As a matter of fact, we should be able to demonstrate the complete deletion of this information now simply by going over to the R2 interface and shutting it down. Or, for that matter, shutting down the R1 interface. Let's try that. Let's go over to R1 and let's simply say shut. We're right in interface configuration mode. And let's say no shut and bring that interface back up. Again, when we bring the interface back up, we can see the normal processes for the link local address advertisement and duplicate address detection. And then we go right back into that mode of sending the router solicitations. But those router solicitations are not being advertised, are they? If we go ahead and we do show IPv6 interface for E0, we're going to see, sure enough, no global unicast address is assigned now. We know that over on R2, we are lacking a necessary command for this feature to work, and that is IPv6 unicast routing over on the R2 device. So in conclusion, let us state a couple of rules. Rule number 1, routers configured with the iOS global configuration command IPv6 unicast routing, like router 2 in our scenario for this presentation, generate the ICMP v6 router advertisement messages. They don't advertise or generate, I should say, router solicitation messages. That's the job of the client in your stateless auto configuration. By the way, you can see section 4.2 of RFC 2461 for more information on this. Rule number 2, routers configured with the iOS interface configuration command IPv6 address autoconfig and not configured with the global configuration command IPv6 unicast routing, like R1 in our scenario, they generate the router solicitation messages only. They are not going to generate router advertisement messages. Again, we can see RFC 2461, specifically section 4.1. As a historical footnote, we should notice that the operation of an IPv6 end station configured with the autoconfig feature is very similar to a workstation configured on a Novell IPX network or an OSI end system using end system to intermediate system routing. It is important to remember that the features of IPv6 that we are studying were developed in the mid-1990s when these other protocols were in use or being considered to be used, such as the case with the ISO's ES to IS. I hope you've enjoyed this video on demand of stateless auto configuration, and again, we'll be covering many related topics in future VODs. In this video on demand, we're going to look at attaining universal connectivity on a per-link basis. We're going to approach this topic, and the topic overall is attaining universal connectivity, and we're going to do this over 3 link types. In this VOD, we're going to look at the simplest of all links in an internetwork, that is a point-to-point link. In a subsequent VOD, we're going to take a look at point-to-multipoint links. We consider this an evolutionary extension of the point-to-point link concept, and we'll be looking at frame relay for an example of point-to-multipoint. We'll also take a look at universal connectivity on a multi-access link, and it's no surprise that we'll be using switched Ethernet for that video on demand. Let's start with a simple point-to-point interface using the default Cisco HDLC encapsulation. We could ensure we're running this default encapsulation by resetting the interface to default using the command default interface serial 1/0 in global configuration mode. I've already done that on R2 for this demonstration. One interesting aspect in performing this configuration is the fact that the interface serial 1/0 here on R2 that we're going to begin working with doesn't have a MAC address. And if we're going to generate, as we know the router will, a link local address and use a modified EUI format for the interface ID, where is the MAC address going to come from? Well, as I'm about to prove to you, it's going to come from a LAN interface. The router operating system literally borrows the MAC from a LAN for the creation of the address. Let's go ahead and do a debug IPv6 neighbor discovery, one of our favorite commands whenever we're manipulating addresses on the router. And let's go ahead and go to the interface serial 1/0 and let's assign an IPv6 address. The address we're going to assign is 2001:1001:2/64. We should see some debug output. First of all, our prefix is added, and then we do a neighbor solicitation for the link local address that was generated. We do duplicate address detection, and we find out that this link local address will be just fine. It is unique on the link. Notice we run through the similar process for our global address, and we assure that the global address is indeed unique on the link. Now, if we do a show IPv6 interface serial 1/0 and we focus in on our link local address, we'll see that it was created just fine even though we didn't have a MAC address. Where did that MAC address come from? Well, I have suggested to you that it came from the fast Ethernet or the LAN interface on this router. Let's check. Do show interface fast Ethernet 0/0, and I want to include the reference of an address. This is a really neat show command modifier that says, okay, don't show me the entire show command, just show me any lines which include ADDR. And by the way, that is case sensitive, the ADDR. And here we can see the address, the MAC address assigned to that interface. CC01:025C:0000. If you look at the link layer address, let me do show IPv6 interface serial 1/0 pipe include link local. Here we got nicely displayed for us the link local address. When you compare it to the MAC address, you see that yes indeed, this MAC address was used to create the modified host interface portion here. We know it adds the FFFE. We can see the C0 that ends this address. We see the C that starts this address, the C01. That's borrowed from this field. So they do some manipulation on this MAC address, but trust me, it is this MAC address that was used for this interface ID calculation. Very interesting stuff. The EUI64 host ID uses the fast Ethernet 0/0 MAC address to create the Serial Interfaces Link Local host ID. And when we do a global unicast address as we did here, that same MAC address is going to be utilized. To avoid any confusion, it's generally recommended that you go ahead and apply your own link local address that will be easier for you to identify. All you got to do this is say IPv6 address FE80:2, for example. I'm on router 2, so I'll end the interface ID with 2. And then you just say it's a link local address. We'll go ahead and do all the unique testing for this. It's going to indeed be unique on the circuit. And now we have a link local address that is much easier for us to work with. In fact, let me rerun that earlier command where we look at just the link local output, and here we can see our new link local address on this interface is FE80:2. Much easier for us to work with. Now let's briefly discuss configuring IPv6 over a PPP interface. We're going to change our encapsulation now to PPP. I'll simply say encap PPP, and we should see the link fail. The link is going to fail because we have an encapsulation mismatch. So let me go over to R1. Let's go to the serial 1/0 interface, and let's set PPP is the encapsulation there as well. If we come back to R2, we should see a status message here any moment, and there it is, indicating the link is back up, and we'll go through all the neighbor discoveries and neighbor solicitations and duplicate address detections on the link. If we go ahead and take a look at, let's get back to privilege mode, let's say show interface serial 1/0, what we should see to confirm we're using PPP is we should see encapsulation set to PPP, and then the particular network control protocol that should be in use, look at this, IPv6CP. So they have a network control protocol designed for IPv6, and we can see it there clearly. One other interesting note for configuring IPv6 over a PPP connection is that unlike for IPv4, there is no peer neighbor route issue with IPv6. In IPv4, this PPP peer route feature generates a host route that can create connectivity issues, but good news, there is no such issues with configuring IPv6 over a PPP link. Let's wrap up our discussion on configuring IPv6 over physical point-to-point connections. We've so far examined two options for the physical point-to-point interfaces, the proprietary HDLC encapsulation and the open standard PPP encapsulation. There are a number of logical point-to-point interface options. Many of them involve tunnel interfaces, and they'll be covered later in subsequent VODs. Before we leave the point-to-point interfaces, I do want to make two brief points. Both relate to link local addresses. Number one, how do you ping a link local address? And number two, how can I configure a point-to-point interface, or can I configure a point-to-point interface using only link local addresses? Well, let's answer both of these questions. A point-to-point link local address is pinged on a point-to-point interface like any other link local address would be pinged. You have to specify both the destination link local address and then the specific exit interface. Let's try it. Over on R2, we set up a very easy to remember link local address. So let me go over to R1 and let me ping it. Remember, it was FE80:2. And remember that these addresses in IPv6 are not case sensitive. When I go to ping the link local address, the router says, wait a minute, I need to know out which interface you need to send the traffic to this particular link. And we say, okay, it is serial 1/0. You cannot abbreviate this. You cannot say S1/0. In the output interface field, you must use the longhand reference of the interface. Why? just don't know. That's how they programmed it. So here we can see we have successfully pinged the link local address that we created on R2. Now let's answer the second question related to configuring a point-to-point interface with only a link local address. Can we do this? Can we skip the global unicast addresses altogether? The answer is, you sure can. You can configure link local addresses exclusively on your interfaces, but please remember when you do this, you cannot reach that interface from a remote network. Many times this is not going to be a problem with our point-to-point interfaces, since they are usually simply router-to-router connections. Look at this illustration. Here we have simple router-to-router point-to-point connections over this backbone, and those could be link local address interfaces only. We'd put routable addresses elsewhere in our topology where we need to access those addresses from some other network. I hope you've enjoyed this video on demand dealing with attaining universal connectivity on a per-link basis, and here we obviously focused on the point-to-point link structure. I think you're really going to enjoy subsequent VODs, if you like this one, that deal with attaining universal connectivity on multi-access and point-to-multipoint links. Let's look at unicast connectivity on a per-link basis, but this time let's go ahead and focus on point-to-multipoint interfaces. And we'll use frame relay for this discussion. Please keep in mind that this discussion is going to be limited to frame relay with IPv6 configurations. Any other questions or issues that you have with frame relay, such as LMI or frame relay encapsulation types, be sure that you access the frame relay class on demand product. Since it's a point-to-multipoint interface, frame relay can reach many destinations over a single interface. This is done by configuring multiple PVCs on a single interface. When you do this, an additional operation must be performed for any unicast traffic, regardless of whether it's IPv4 or IPv6 traffic. Unicast addresses must be mapped to specific DLCs. Since a unicast packet must be delivered to one and only one destination, it is not replicated out multiple frame relay PVCs. Unicast traffic can only be forwarded out of one and only one PVC. Now, if this is the case, how is the correct PVC selected? Two possible options exist for IPv6. One is that we configure a static option using the frame relay map iOS configuration command, and the second option is a dynamic one, where we apply the IPv6 inverse neighbor discovery protocol. This is fully documented in RFC 3122 and is roughly equivalent to the version 4 inverse ARP functionality. We're going to limit our discussion to only the static option using the iOS frame relay map interface configuration command. So whether you do it statically or dynamically, you need to map an IPv6 unicast address to a DLC. A unicast IPv6 packet needs to be forwarded out a physical frame relay interface, but the question is, which DLC will the unicast IPv6 address use? It can only use one of the DLCs, but again, which is it going to use? And you can see that question is presented here in this illustration. With a Cisco router, the answer lies in statically mapping an IPv6 address to a specific DLC using the frame relay map command. When a frame map command is entered, unicast IPv6 addresses can be explicitly mapped to specific DLCs. In hands-on presentations that we'll perform in this video on demand, you will see what happens when such mappings are not supplied. It is important to note that both routable unicast addresses as well as link local addresses must be mapped to specific DLCs using frame relay map statements. So let's take a look at a topology here, and let's see if we can ping a neighboring frame relay attached router. Now, when we do a test like this, we're going to go ahead and we are going to run a couple of debugs. Let's do debug IPv6 packet, and let's also do debug frame packet. So we've got these debugs turned on. And now what we're going to do is we're going to try and ping from R1 the frame relay interface IPv6 address on R2. Let's try it. Ping 2001:12::2, and let's see what happens. Aha, look at this. We have encapsulation failed messages occurring. We have also encapsulation failed frame relay messages occurring. The frame relay message says no map entry link, and the IPv6 message says encapsulation failed, resolving next hop on interface, and we have source and destination selected, but again, we have the fact of both of these message types tell us that encapsulation has indeed failed. So we attempt to forward it out the correct interface, that's serial 1/0, but obviously we have an issue with the encapsulation. Usually when you see messages like this, it is due to a lack of a Unicast address to frame relay DELSI mapping. To look for such mappings, we can enter the command show frame relay map, and notice that we get no response. So we should be able to add a mapping and make this work. Let's go into interface configuration mode for the interface, and let's say frame map IPv6 2001:12::2 is the IP address on R2, and we're going to say take DELSI 102 to get to that particular destination. So now we have added a frame relay map statement for that destination. Let's confirm this with the show frame relay map command. And here we can see that we do now have an active static mapping for the 2001:12:2 address. Let's go ahead and try the ping again now that we've added this mapping. So we are not meeting with success in the ping. The ping is not successful, but interestingly here, we are not having an encapsulation failure. So no encapsulation failure this time whatsoever. Let's go over to R2 and let's go ahead and turn on debugs over there. Debug IPv6 packet, debug frame packet. Let's now go over to R1. Let's try the ping again, and let's see what's happening on R2. Oh, here we see that encapsulation is failing on this side. What's happening is, on this side we're having encapsulation failures because R2 is attempting to respond, but R2 is lacking the appropriate mapping for R1. Okay, great. Let's go into the interface on R2, and let's say frame map IPv6 2001:12::1, and we need to take DELSI 201 as you can see from the diagram. So now we have added a frame mapping on R2 for R1. Let's try our ping again. We'll go over to R1 and we'll retry the ping, and now we meet with success. Now that there is a proper mapping, specifically R1 needed a frame map statement for R2's frame relay address, and R2 needed a frame relay map statement for R1's frame relay address for return path traffic. This behavior is exactly the same as IPv4 unicast forwarding over frame relay. IPv4 packets need similar unicast to DELSI frame mappings. What is different between IPv4 and IPv6 when configuring them for frame relay unicast connectivity? Two big differences. Number one, with IPv6, you must also configure mappings for link local addresses. And this is because link local addresses will oftentimes be used by control plane operations, such as routing protocols. Also, the link local address is used as the next hop address for any routes installed in a routing table by an interior gateway protocol. If the next hop link local address is not reachable because it's not mapped to the correct DELC, the remote network will be unreachable. IPv4 has no similar concept of link local address, so this is a uniqueness to IPv6, and it's a big difference in v4 versus v6. Now, the second big difference between v4 and v6 when it comes to frame relay is this fact. With IPv6, you must explicitly enable IPv6 unicast routing when you attempt to ping from one spoke to another spoke on a hub and spoke frame relay topology. By the way, let me go ahead and review with you and show you the link local mapping issue. As an example here, we're going to configure a simple OSPF for v6 configuration over the frame relay interface between R1 and R2. Please note that OSPF for IPv6 is completely covered in a separate video on demand. We're going to use a basic OSPF configuration because certain OSPF functions use the link local address for packet exchange. So let me go to the R1 interface here, and let's set it up for OSPF for v6. We're going to do everything, but we're omitting the frame map command for the link local address. So I'm going to go into the interface, and I'm going to go ahead and say IPv6 address, and I'm going to set my own link local address. We know that we can do this. I'm going to say IPv6 address, and I'm going to specify a very easy to recognize link local address. And let me go ahead and turn off the debugging here. So as you just saw, and let me show you that with a show IPv6 interface serial 1/0, we have just reset the link local address, so it will be very easy for us to recognize as the link local address belonging to R1 serial 1/0. This will also make it very easy for us to do our map statements. Alright, now let's go back into the interface serial 1/0, and I am going to say IPv6 OSPF neighbor FE80::2, and that's a link local address that we are going to set here in a moment on R2. And then finally IPv6 OSPF 1 area 0. We're just going to try and set area 0 between these two. Oh, let's do IPv6 unicast-routing, and then we'll be able to issue that command IPv6 OSPF 1 area 0. Okay, so notice we've done a resetting of the link local address here, and we've set up our OSPF statements. I'm going to go over to R2, I'm going to turn off debugging, and I'm going to say, for the serial 1/0 interface, IPv6 address FE80::2 is its link local address. Now our OSPF commands. Actually, let me skip out and set up IPv6 routing. Let me go back under the interface and let me say IPv6 OSPF neighbor FE80::1 IPv6 OSPF 1 area 0. And now we're going to sit here and we are going to wait for the adjacency to establish. And we're going to be waiting for a long time. Why? Because we are lacking frame relay mappings for the link local addressing. Let's prove this. Let's go into the interface once again, and let me say frame relay map IPv6, and here on R2 it will be FE80::2 1 out del C 201. This is the frame relay mapping for the link local address that we were missing. Now, by the way, the broadcast keyword will allow broadcast and multicast traffic to flow on the circuit, and as we've been trained in the frame relay module, you only need to use this broadcast keyword on one frame relay mapping for that circuit. Don't use it on multiple mappings. So let me show run interface serial 1/0, and we can see the final configuration here. Notice I have two frame relay map statements that reference del C 201. Make sure we only put the broadcast keyword on one of those two statements. So there's the R2 configuration. Let's go in here and finish up the R1 configuration. I'll say frame relay map IPv6 FE80::2 out del C 102 broadcast. And now that we have the frame relay map statements in for the link local addresses, like magic, we see the formation of the OSPF neighborship. So the neighborship has just come up as a result of the proper configuration of these IPv6 point-to-multipoint interfaces. So in conclusion, we have a couple of things to really watch out for in the IPv6 point-to-multipoint environment, especially involving frame relay. Watch out for the additional mappings that you need to put in place for the link local addressing on your circuit. And something that we didn't show you, but I want you to be very aware of, is when you are configuring an IPv6 hub and spoke type of topology, and you want one spoke to be able to communicate with another spoke through a hub router, make sure this hub device is configured with the IPv6 Unicast routing command. This is a requirement because that hub device is going to need to encapsulate and de-encapsulate as well as route traffic from one spoke to the other. So, very, very interesting, this look at IPv6 in the point-to-multipoint environment, and you will see more of this when you look at our video on demands that deal with the routing protocols, because some of the routing protocols will go ahead and do over frame relay, and we'll see that if you are missing a link local frame relay map statement, you're going to have problems with reachability, because remember, another interesting thing here in v6 is that routing protocols are going to use link local addresses for the next hop. It's now time for us to expand our discussion of attaining unicast connectivity on a per-link basis to multi-access links. Specifically, we're going to limit our discussion to a switched Ethernet network using a Catalyst 3560. We're going to just take two simple routers here, R1 and R2, and we're going to connect them via a LAN switch, and we're going to put them in the same VLAN with each other. Obviously, configuring an IPv6 address on an Ethernet interface is a very simple task. So what is the primary difference between attaining unicast connectivity on an Ethernet segment as opposed to a frame relay or point-to-point connection? One difference is the use of the neighbor discovery process and the neighbor discovery table. With a multi-access interface, the neighbor discovery process acts as the IPv4 ARP process. It is very important to note that there is no ARP process with IPv6. The ARP replacement process is the ICMP neighbor discovery process. For every remote unicast destination address, there must be an IPv6 unicast address to unicast MAC address mapping in the show IPv6 neighbor table. Let's take a look at this at the command line. Let me go to R1 and let me go ahead and do the show IPv6 neighbor command. When I type the show IPv6 neighbor command, unicast IPv6 addresses are mapped to unicast MAC addresses in a manner that is similar to an IPv4 ARP table. To reinforce this idea, let's take a look at the IPv4 ARP table. To do that, we'll just type show ARP. So what is the difference between the IPv6 neighbor discovery process and the IPv4 ARP process? The ARP protocol is separate from the IP protocol. It uses a broadcast destination address in ARP request messages to map an IPv4 Unicast address to an Ethernet Unicast MAC address. Again, it is important to note that the ARP protocol does not use an IP header when ARP requests and replies are generated. The ARP replacement for IPv6 is not separate from the IPv6 protocol. It involves two ICMP message types that are unique to IPv6. The ICMP v6 neighbor solicitation message, type 135, and the neighbor advertisement message, type 136. These two ICMP message types are encapsulated inside of an IPv6 header. While IPv4 ARP messages use a broadcast address as the destination, IPv6 neighbor solicitation messages use a special multicast address called a solicited node multicast address. The solicited node multicast address begins with a specific prefix that we will see in a moment, and then the last remaining 24 bits of this multicast address are extracted from the destination unicast address specified in the ICMP v6 neighbor solicitation message. By the way, this address is also discussed in our IPv6 multicast video on demand, as you might guess. We can actually see the solicited node address with the show IPv6 interface command. Let's try it here at the command line. I'll say show IPv6 interface Ethernet 0. Notice we can see this solicited node multicast address. They begin FF02, and then they're going to end with, actually, as we can see here, with 24 bits borrowed from the link local address. So we're borrowing bits from the link local address to create this solicited node prefix. We can actually prove this. Let's go to this interface and let's say interface E0 IPv6 address, and I'll say FE80 A BC link local. So what we're doing is we're creating a new link local address for this interface. Now if I do a show IPv6 interface E0, we see that we have our new link local address, and we ended it with ABC. And if we look down here, we see that we have our new solicited node multicast address. It also ends ABC. Now let's take a look at this IPv6 neighbor discovery process using two routers over a single Ethernet segment. Let's begin with the following simple configurations on routers R1 and R2. All we're going to do, if you show run interface Ethernet 0, is configure an IPv6 address, which I've done. So we have an IPv6 address on R1 and R2. That's all we need for configuration here. When we go ahead and ping one from the other, for instance, ping 2001:1:2, so I'm pinging from R1 to R2, we are going to create mappings in the IPv6 neighbor table. And here you can see the mappings. Notice that there are two different IPv6 addresses referencing the same exact MAC address. So we have two entries in here referencing the same MAC. What are these two different addresses? Well, sure enough, one is the global unicast and the other is the link local. So there we see the global unicast and the link local for this particular destination. Notice that in this case we have one marked as reach and one marked as delay. If we go over to R2 and do a show IPv6 neighbor and look at the neighbor table over there, we see that here we don't have any marked as reach. we have entries marked as stale. What's going on? Well, first of all, this stale state is attained when a listed address that was formerly in a reach state has not been used for a period of time that exceeds the IPv6 configurable parameter of IPv6 neighbor discovery reachable time. Interesting. This would look like this at the command line. So we can configure an IPv6 neighbor discovery reachable time value. And notice this is going to be entered in milliseconds. So if we have a stale state, we've exceeded this time. We haven't used the entry in that time. If we have a reach state, we have used the entry within that time. Now let's attempt to ping a non-existent IPv6 Unicast address on the segment, and let's look at the neighbor solicitation messages that result. So let's go ahead, we can do it right here at R2. Let me go ahead and say debug IPv6 neighbor discovery. And now let me go ahead and ping a non-existent address. I'll ping 2001:1:10, and we'll repeat just once. We'll just send one packet, and we'll see the messages that result. We're, of course, not going to meet with success. Now notice what happens here. We see that there are 3 neighbor solicitation messages generated for this address, and then we see that we go through some state changes, don't we? We have a delete state and an incomplete state. Initially, the IPv6 neighbor discovery went from, let's scroll up to look at this. Initially, it went from delete to incomplete, and then after the 3 neighbor solicitation messages, it went from incomplete to delete. So, very interesting. We have these different states, and we see that we're incomplete. We're trying to attain the correct information, the resolution of layer 3 to layer 2. When we cannot, we go from the incomplete to the delete state. So these states are named well. They make a lot of sense. Let's try this again, but let's use a different tool. Let's go ahead and turn off the debugging that we were doing there, and let's do a debug IPv6 packet detail. Debug IPv6 packet detail, and let's initiate that ping again. Let's look at these messages. Alright, when we look at these messages, we see that 3 packets go out using the solicited node multicast address as the destination address. These 3 packets are the IPv6 neighbor solicitation packets. So look at this. We can see that we are using that solicited node multicast destination address as the destination for these packets. And that would make sense. We're trying to do the neighbor solicitation process so we can build this resolution table, and here we can see the destination of these packets is indeed the solicited node multicast address. Something else that we can do, in addition to having this address resolution occur dynamically, is we can build static mappings for the IPv6 Unicast address to an Ethernet MAC address. You can build a static mapping. You can go in and you can say, in global configuration mode, IPv6 neighbor 2001:1:10 Ethernet 0, and then provide a MAC address. So you can do static mappings in the table, and that is the syntax that you would use to do it. If we verify this with the do show IPv6 neighbors command, you're going to see that the entry that we manually put in the table is not going to feature an age value, and it's going to be permanently in that reach state. So very, very interesting. We actually have two options for mapping an IPv6 unicast address, therefore, to a MAC address, and one is dynamic and one is static. Once again, very important to know your configuration options when it comes to IPv6, or for that matter, any topic. Now, we used a 3560 to provide the switch connectivity between these routers. Let me stress to you that while the 3560 does support IPv6, it's not configured to do so by default. What we need to do to provide IPv6 support on the 3560 is to go ahead and utilize the SDM command. The SDM command stands for Switch Database Management. So we issue the command SDM prefer dual IPv4 and IPv6 routing. We then reload the 3560, and then we can confirm this configuration with the show SDM prefer command. So if we want the 3560 to fully support IPv6 routing, we need to make this configuration change on the 3560. Well, I hope you've enjoyed this video on demand regarding Unicast connectivity and specifically a multi-access link, and we look forward to your participation in future video on demands. Let's begin this block on routing for IPv6 by taking a look at certainly a way that we can route on the equipment, and that is static routes. The manual configuration of route information in the routing tables. You may think, when would I ever do this? We know there are many times that static routes are going to become important in a configuration. We'll see them in tunneling configurations. We see static routes in maybe a branch office headquarters type configuration where we don't need the overhead of a routing protocol. Incidentally, we must be careful with static routes in the CCIE lab exam. Many times they are completely prohibited except if explicitly stated we can use them. So let's read the overall rules about static routes, and then let's be very careful to look for wording in the exam that indicates we might need to use them. Here you can see the v6 static route syntax, and it follows very much from v4. Instead of IP route, we say IPv6 route, and then we specify the prefix and prefix length, and then we'll specify either an interface, a next hop IPv6 address, or both. In addition to this, we have the administrative distance value that we can assign, and some additional keywords like unicast, multicast, or tag. Those will come up where appropriate in the particular VODs. So let's take a look at a directly attached static route syntax. We say IPv6 route and then the address and prefix length. In this case, I'm saying 2001 CC1E /32 is the prefix we are interested in training the router how to get to. Here, because we're using a directly attached static route syntax, all I say is, you know what? In order to get to this particular prefix, go out serial 0/0/0. The destination, therefore, is assumed to be reachable right out this interface. So notice we don't specify a next hop. The packet destination address is used as the next hop. In order for this static route to be valid and installed in your v6 routing table, the interface must be in the up state with v6 enabled on the particular interface. Another option would be to do a recursive static route. Here you can see I'm specifying destination prefix, but I'm saying to get there, go ahead and take the next hop 2001:12::1. So we provide a next hop IPv6 address. It's called a recursive static route because what the router will now do is when this destination is triggered, when this destination is seen in the incoming packet, it will then take a look at its routing table and determine the appropriate interface based on the next hop address. In order for this static route to be valid then, the router's got to be able to do this. It's got to take a look at the next hop of 2001:12, and it's got to be able to figure out what interface is appropriate for this particular traffic. A fully specified static route includes both an interface reference as well as the next hop reference. So here I've got the same prefix, but I'm saying to get to this particular prefix, use the Ethernet 0/0/0 interface, and oh yeah, by the way, out that particular interface, you'll be looking for a next hop of 2001:12::1. This is ideal when the output interface is multi-access, and there could be multiple next hops reachable out that particular output interface. Also, floating static routes are still around in IPv6. You're probably familiar with these from a v4 routing environment. With a floating static route, we do a neat trick. We give an administrative distance for the static route, and we provide an administrative distance for the route that is higher than the administrative distance that would be found for a dynamic routing protocol method to get there. This is a nifty trick indeed, and can be used as a backup to a dynamic routing protocol. You see, this static route will not be installed in the routing table unless the entry for the dynamic routing protocol is missing. If that goes missing because we have a link failure or something along those lines, then this route with the worst administrative distance would be installed in your routing table. So it's a cheap, efficient way to do backup routes. Well, let's go ahead and experiment with some static routes between R1 and R2. What I've tried to build here is get you thinking of like a headquarters to branch office type situation. Notice here at headquarters, represented by R1, we have several different v6 networks, and then we're connected via a point-to-point serial interface to R2. R2 is a little branch office router in this case, and notice it only has one v6 network out there other than the link to headquarters. So what we'd like to do is configure full reachability in this topology using static routes. Let's start on R1, the headquarters router. We'll enter global configuration mode and we'll say, all right, we want to turn you into a v6 router. We'll use the IPv6 Unicast-routing command. Next, we need to train R1 how to get to that single network off of R2. So I'll say IPv6 route. I'll say the network is 13/64, and we'll say it's directly attached. We'll say just take traffic and send it out serial 1/0 in order to get to that network. And guess what? We are done here on R1. We can verify this configuration with the show IPv6 route command. And what we're looking for in the v6 routing table is to make sure we have a static route entry that instructs the router how to send traffic to the 13 network. Let's go over to R2 now. This is the branch office router. And on R2, I'll say IPv6 Unicast routing. You are now a router for v6 traffic. And on R2, what we're going to do is we're going to use a default static route. We're going to say, look, there's lots of networks that are attached to headquarters. In order to get to any of them, just send your traffic out the serial 1/0 interface. So I'll say IPv6 route ::/0. We're saying this default static route syntax is that any network, and we specify any network using simply ::/0. And now I'm going to say, go ahead and send the traffic out serial 1/0. All right, so there's our v6 route for a static route. If we don't have awareness in the routing table how to get there specifically, go ahead and use this default static route. If I do a show IPv6 route, we will see that default static route in the routing table, and that should provide reachability to any of these networks over on R1. So we're ready to test. We'll go to R1 and I'll say ping 13.13.1. Can we reach the network that is out there at the branch office? Look at that, we sure can. It's perfect. Let's go over to R2. Can we reach the 11 network? Yes, we can. And if that worked, I'm feeling good about the 10 network. Can we reach the 10 network? We sure can. So here we completely provide full reachability between headquarters and the branch office, all with using just a couple simple static route entries.